All right, so we're in section 4.4, and we're talking about the fundamental theorem of calculus. And what this section is going to do is it's going to show us the connection between the indefinite integral and the definite integral. If you recall, the indefinite integral we introduced in 4.1, and we defined it to be the most general antiderivative for some given function, whatever your integrand is. So at that point, we were only thinking of that integral symbol as representing the antiderivative for a function. Then in the previous section, 4.3, we defined the definite integral, where we used the same symbol, the same integral symbol, but we put some values in there, the upper and lower limits of integration. And that's how we knew we were looking at a definite as opposed to an indefinite integral. And we defined that to represent the area under a curve over the interval given by those limits of integration, the a and the b. Those are two seemingly completely unrelated topics or concepts. It turns out that they are related, as hopefully you would have expected, because it would be weird if we used the same symbol, the same integral symbol, for two completely different things. So they are connected, and it's in this section that we establish that connection. So to lead us into this, let's suppose that capital F of x is some continuous function, and let's also suppose that little f of x is the derivative of big F of x. This tells us two things. One, it means that capital F is an antiderivative for little f, and it also means that little f can be interpreted as the rate of change in capital F with respect to x. Remember, if little f is the derivative of big F, so little f is a derivative, we interpret derivatives as rates of change in a function, right? So with that said, in section 4.3, when we were looking at definite integrals, we saw that the definite integral, although it does represent the area under a curve, we found that you can interpret it in a different way. You can interpret it as the net change in an integrand if that integrand is the derivative of something. Specifically, it represents the net change, sorry, not in the integrand, but in the function that f would have been a derivative of over an interval. In this case, the definite integral from a to b of little f would represent the net change in big F over that interval ab. And we talked about why that was back in 4.3. But what we didn't really talk about was that you can evaluate the net change in a function if you know that function, if you know what big F is equal to. It's easy to do that. All you have to do is find the values of big F at each endpoint in that interval, and then subtract f of the larger endpoint minus f of the smaller endpoint. That's what subtraction really is it tells us the change in a quantity from one place to the next. So this is how we would also evaluate net change. And because these are two different ways of evaluating the same thing, they must be equal to each other. And this result is what we call the fundamental theorem of calculus, which is arguably the most important theorem in the entire subject of calculus, which is why it got the name that it got. To be a little bit more specific, though, if you see the fundamental theorem of calculus shown here, we are specifically talking about part 2. Part 2 is the result that we just talked about. So I'm going to read this so we can see it as a part of this theorem. If f is a continuous function on the interval ab, and if capital F is any antiderivative of little f, then the definite integral from a to b of little f of x dx is equal to big F of b, the upper limit, minus big F of a, the lower limit. And what this does is it tells us how to evaluate definite integrals without having to use the techniques that we were using in 4.3. In 4.3, we were very, very limited in how we could approach solving a definite integral. We basically only had two major approaches. One was approximating definite integrals using Riemann sums and that rectangular approximation method. That method is time-consuming, and it doesn't even give you an accurate answer the majority of the time. It's an approximation tool. So it's much more preferable to have an exact answer to an approximate one if possible. The other way that we approached definite integrals is if the graph of our function took on very specific shapes, we could use geometric area formulas. But the majority of the time, that's not what your graph looks like. So that's rarely an option in practice. The fundamental theorem of calculus will work anytime the function that we are integrating is continuous and if we are able to find an antiderivative for that function, because that's what big F is in relation to little f. So that is extremely, extremely powerful and useful. And let's illustrate its usefulness in this example. Before I do want to mention or acknowledge the fact that I didn't say anything about part 1 of the fundamental theorem. Between these two parts, part 2 is by far the more important part. In a full course on calculus, I would start by teaching you part 1 of the theorem. And then the primary role of part 1 is to serve as a step in the proof of part 2. So part 1 is kind of a stepping stone to part 2, and part 2 is the thing we really care about with the fundamental theorem, for the most part. Because we're not focusing on rigorous proof of things in this class, we approach this from a different perspective. We are going to talk about part 1 of this theorem, but we're saving it until the end of this lecture. So I'm going to return to this later, but for now we can just go past it. Let's evaluate some definite integrals using the fundamental theorem of calculus, starting with part A here. So for part A, I'm evaluating the integral from 1 to 4 of x squared minus 4x all over the square root of x. So first of all, we've seen integrals of this type before. What we want to do is put it in a different form so that it's easier to find an antiderivative. Because again, with the fundamental theorem of calculus, what we're looking for first is an antiderivative for that function in there. I can write my denominator as x to the 1/2 power, and then I can split this up into two rational expressions, x squared over x to the 1/2, which simplifies to x to the 3/2 power, minus 4 times x over x to the 1/2 power, which is x to the 1/2 power. You've seen me do this before. You've seen this approach. So this is nothing new. Now I'm looking for an antiderivative of this. And this is an easy antiderivative to find because we are just doing the power rule in reverse. Remember, we add 1 to the exponent, which is going to give me x to the 5/2. And then we multiply that by the reciprocal of what we just found. Okay? This guy right here, minus, I'm going to add 1 to the exponent, which is going to give me 3/2, multiplied by the reciprocal of that, which is 2/3, but I already had a 4 there, so 4 times 2/3 is 8/3, like that. Okay? Now, this is the antiderivative, or it's an antiderivative for this integrand. But now what we want to do is show that we're going to use these limits of integration with the fundamental theorem of calculus to get an actual number out of this. Remember, this should represent an area under a curve, which should come out as just a single real number, not a function. So here's how we do this. We use this notation. I'm putting square brackets around this, and then I'm going to put the numbers 1 to 4 here, 1 to 4. The fundamental theorem of calculus says that I want to take the upper limit of integration, plug it in here, and then subtract from that the lower limit of integration after being plugged into there. So I'm going to do this. 2/5 times 4 to the 5/2 power minus 8/3 times 4 to the 3/2 power. So notice I've plugged the upper limit of integration into that, and then I'm going to subtract the thing I get from plugging the lower limit of integration in. It is extremely important that you put parentheses around this whole thing first. People oftentimes forget to do this, and what ends up happening is they will apply this minus sign to only the first term of the two terms that appear here, and they get a wrong answer. I've seen this over and over and over again with calculus students. Put the brackets around that. The only time you don't need to worry about brackets is if your antiderivative has only one term. But if it has more than one, put brackets there. This is going to become 2/5 times 1 to the 5/2 power minus 8/3 times 1 to the 3/2 power. Okay, now it's some arithmetic that we have to deal with. So remember, anything to the 5/2 power means I'm taking the square root of that number and then I'm cubing it. The square root of 4, let's do this one. 5/2, square root of 4 is 2. And then if I do 2 to the 5th power, that's 32 times this 2, that gives me 64. So I have 64/5. Here, the square root of 4 is 2. 2 cubed is 8. So 8 times this 8 is also 64. I get minus 64/3. Okay? Now this minus has to get distributed to everything. So this is going to become a minus 2/5, and 1 to any power is just 1. So I can just write that as 1 times 2/5, which is 2/5. And then here, same thing. This is 8/3 times 1, so I have 8/3, but that has a minus, and another minus would have distributed to it, giving me a plus 8/3. Okay, I have some fraction arithmetic that I need to do here. So look at things that have common denominators first. I have 64/5 minus 2/5, which is 62/5. And then I have negative 64/3 plus 8/3. So that's going to give me minus 56/3. Now I'm going to get a common denominator. So 3 times 62 is 186. And 3 times 5 is 15. Minus, I have to multiply this by 5. Let's see, that's 250 plus 30, so 280 over 15. Let's see if I could squeeze this in here. If I do the subtraction, I'm going to get negative, what would that be? Negative 94 over 15. I believe that is correct, right? Yeah, negative 94 over 15. Managed to kind of squeeze that in there, negative 94/15. Okay. I didn't work this one out ahead of time, so if I made an arithmetic error in there, sorry about that. Check your answers. Check my work. Make sure I'm doing this correctly, because I make mistakes too. But that's part A. Let's take a look at part B. I'm going to go like this to kind of separate the work out. Part B. Here's another one. I want to find the definite integral from 1 to e of e to the x minus 6 over x. Well, that's not too difficult. I don't need to simplify the integrand at all, 1 to e. If I'm going to do anything, and it's not even something I would normally do, but I could do it here. I could take the 6 and put that out front and write this as 1 over x. Just kind of to put that in a form that I recognize. 1 over x, I know that its antiderivative, or an antiderivative, is the natural log. E to the x is its own antiderivative. So I get e to the x minus the 6 stays put, 6 natural log of x. And technically, it would be the absolute value of x, right? I can put that in there. But because I'm plugging in numbers that are already positive, the absolute value won't actually do anything. So I'm going to put it in there just for the sake of accuracy, but I'm also kind of making note of the fact that it's not going to matter. Now we plug in these values. So I plug e in for x. This becomes e to the power of itself, e, minus 6 times the natural log of e, minus, remember, put square brackets around this, e to the power of 1, minus 6 times the natural log of 1. Okay? Now, the natural log of 1 is 0. This whole term will go to 0. Natural log of e is 1. Remember, the natural log is the log with the base of e, so that would equal 1. This simplifies down. I get e to the e minus 6, because that's negative 6 times 1, minus e to the first power, which is just e, so minus e. And then that minus changes that to a plus, but because it's just 0, it's not going to change anything. And so this is what my answer would look like. E to the e power minus 6 minus e. Okay, let's do one last problem. C. I want to integrate from -1 to 0, x to the 5th power times 3x squared minus 4 dx. We've seen integrals like this before. It helps to distribute the x to the 5th power first. So I'm going to do this. X to the 5th times 3x to the 2nd power would be 3x to the 7th. Minus 4, I'm going to get minus 4x to the 5th. Like this, okay? Now, find an antiderivative. So add 1 to the exponent, that would be 8, x to the 8th. Then multiply by the reciprocal of that, 1/8. I have a 3 out there. 3 times 1/8 is 3/8. Minus 4x to the 5th. So what's going to happen here? I'm going to add 1 to the exponent, x to the 6th. And then I'm going to divide by 6 or multiply by 1/6. 4 times 1/6 is 4/6 or 2/3 after simplifying. From -1 to 0. Okay? Now we plug in our limits of integration. So notice here, if I plug zeros in, I'm going to get 0 times 3/8, which is just 0. I'm going to get a 0 here. -2/3 times 0 is just 0. Minus, put square brackets, 3/8 times -1 to the 8th power minus 2/3 times -1 to the 6th power. And notice I put square brackets around the value that I would be getting from plugging my lower limit of integration in. This is clearly just 0. And when I raise -1 to an even power, that's equal to 1. And 1 times these fractions would just be those fractions. And then when I distribute this negative in, I'm going to get opposite signs. So this becomes -3/8 plus 2/3. Okay, let's get a common denominator of 24. So I'd be multiplying this by 3, -9 24ths. Multiply this by 8 plus 16 24ths, which would be equal to 7 24ths. And that's what I got for that one. Okay, so that's the fundamental theorem of calculus. Again, this is combining two things that we've done in chapter 4. It's combining the indefinite integral with the definite integral. Specifically, we are evaluating definite integrals, but we are using antiderivatives to do that, and then plugging our limits of integration into the antiderivative that we find, and then doing some subtraction. Now, one thing you'll probably notice is that when I found these antiderivatives, I never put a plus c there. I know in 4.1 and 4.2 we were putting plus c's every time we were finding an antiderivative for something, or an indefinite integral. The reason we're not doing it here is because it's not asking for the most general antiderivative. In fact, if you read part 2, it says in f is any antiderivative of f. So remember that plus c is there to account for all possible constants that I could add to an antiderivative, because that would generate another antiderivative for the original function. But if we just let c equal 0, that will simplify what we're writing here. It turns out that whether c was 0 or 10 or pi or any other number that we wanted to assign to that plus c, it would have canceled itself out when we do this subtraction anyways. So there's no real reason to put a plus c in there if it's always going to cancel itself out and play no actual role in the answer that we get. So don't worry about the plus c's, just look for the simplest or most straightforward antiderivative for the function you're working with. And that would specifically be the case where we set c equal to 0. Okay, so that's all I have to say about that. I'm going to end this video here. In part 2, we're going to do some more examples.